In this video, I'm going to look at a problem that uses Newton's law of cooling to find a model for a temperature change. The situation would be you have something that's very hot, hotter than the ambient temperature, or it could be colder than the ambient temperature. And what you'll get is if you start with something hot, it will have an initial temperature up here and it will asymptotically approach your ambient temperature. So ambient temp, we might call that room temp. What we'll call that mathematically is TS, and S is, I think, just for surroundings. And so this would be Newton's law of cooling in effect. We start up here at an initial temperature, that's T at time 0, and then we slowly lose that heat to the surroundings. That's Newton's law of cooling. Now, we could also have Newton's law of warming if we start down here below at a cold temperature. So either one would be true. The way we're going to model that is temperature at time t, and so capital T is temperature, lowercase t is time, is AE to the KT. You can use T0 here. I frequently do that, but really T0 would be initial temperature, and that actually isn't going to go there. So then we add the surrounding temperature. So if we did have our initial temperature, we would plug in a 0 and see that that's A plus TS. So the initial temp would be T at time 0. Plug in a 0 for the exponent. That's going to be 1. It'll be A plus TS. So let's say in this problem, we've got a frozen. In the homework, you have a hot dog. So I'll do the same thing. You have a frozen hot dog. It could be any item at negative 30. And I'm going to go just a little bit lower than the homework. This is negative 33 degrees Fahrenheit. Is placed in a room at 68 degrees. And then what we would need is kind of a reference point. So different rooms are going to behave differently. If there's a lot of air circulation, for example, things like that. So we do need a reference point. Let's say after 20 minutes, it reaches 25 degrees. Oops, that's a percent, 25 degrees. Then I would need to know a couple things, like for example, what is K? What is the temperature after, let's say, 45 minutes? And then how long will it take to reach 50 degrees? So kind of the important information that we have here is that we're starting at an initial temperature, T0, of negative 33. I already said that's going to be A plus TS, so negative 33 equals A plus the temperature of the surroundings or the room, which is 68 degrees. If I subtract 68 from each side, I can figure out my A. So that's negative 101. Now I can set up my model T of T equals negative 101 e to the KT power plus 68. Now I'm going to use that reference point. The reference point is after 20 minutes, it's 25 degrees. So one thing I'm going to note is that T equals minutes. That could vary depending on the problem. So this one said after 20 minutes, it was 25 degrees. So T of 20 is negative 101 e to the K times 20 plus 68 equals the temperature of 25 degrees. Now I want to solve for K. So I'm going to subtract 68 and divide by negative 101. Let me do that on the next page. So all I really need is the right side of this. And I'm going to rewrite that as 20k. $25. So I'll solve I'll isolate the exponential algebraically. Start by subtracting 68. That'll be negative 43, 25 minus 68. And I'm just going to check my work along the way. Divide by negative 101. Now I could write this as a decimal. It's going to be much better to leave it as a fraction. Now you can check and see if it will reduce. I know this one won't, but if it does, you'll be able to see it there by converting that to a fraction. So that's going to be the simplest way I can write my exponential. Now I would want to take the natural log of each side or use the definition of the natural log. The natural log is going to make it so that 20k equals the natural log of 43 over 100. So the definition of the natural log is an inverse of e, so it's going to swap kind of the inputs and outputs around. Now dividing by 20, I've got my k. Make sure that you're dividing outside of the natural log or you're dividing the result. So my k value is natural log of 43 over 101. And then that result divided by 20. It should be negative because it's a decay function. A decay function would be like, 1/2 to a power. But since our base is bigger than 1, we need a negative exponent to sort of counteract that. So the best we can really do is approximate it. You can use this approximation, negative 0.0427. However, I would continue to use the full value of k within the model. So to make predictions and things like that, I would recommend using the full value of k. So now we've got our temperature function. I'm going to keep writing this as k, so I don't have to fill all of that in. And now I can make some predictions. So what was that? Plus 68 here. So the next question asked, let's see, what's the temperature after 45 minutes? That would be T of 45. Now is where it really helps to use Desmos graphing calculator. I'm going to define my function. I'm going to put k here and I'll define that in a separate line. I can add a slider for k, and now I can set k to be my ln 43 over 100 divided by 20. Uh, 43 over 101, actually. Okay, and so that makes this a little simpler. It puts that kind of in a separate spot, but it also gives us the full precision of it. So we can test this function out. We know for a fact that after 20 minutes, it should be at 25 degrees. So that works great. Next, we want to know after 45 minutes, what will it be at? About 53 degrees. And then the last question said how long to reach 50. Now this is one where using the graph can actually help you out a lot. So I zoomed out, there's my curve. A nice way to frame this would be go from like -5 to 60. So look at the first hour. The reason why I go negative is so I can still see the y-axis there. Sometimes it helps to even go a little bit farther negative. For the y-axis, it starts at a temperature of negative 33. So let's start at negative 35 on here, and then it's going to end somewhere around 68. So I'll go to 70. So that's going to really frame it well. You can even zoom out a little bit more than that. Now we want to know how long it's going to take to reach a temperature of 50. The temperature is on the y-axis, so we want to know when y is 50, and that's going to happen after over 40 minutes, about 40 to 41 minutes. If we wanted to do that by hand, we would need to set our equation or our model equal to that value of 50. So either way, I would definitely grab a calculator to find T of 45. That was about 53.2 degrees Fahrenheit. And then the other one is basically how much time will it take to get to 50. It should be a little less than 53. We're going to have to set that equal to the model and solve for T this time. Now K is known. I'm just going to wait to input that till later. So let's solve this for T. Now I'm going to isolate again. It's going to feel like I already did this before. And that's because it's pretty much the same steps until the very end. I'm going to solve for T instead of K. Divide by negative 101. And so now I'm going to get e to the kt equals 18 over 101. Feels very familiar. And then ln of 18 over 101 equals kt. In other words, t equals ln of 18 over 101 divided by k. And now I can put in my k. K was, circled back here, ln of 43 over 100 divided by 20. So if I take ln of 18 over 101, which I can do right here, divide that by k, which I already defined here, I get that 40.396, or about 40.4 minutes. You can also see what that looks like if I just type the full expression there. So it is important. I usually put that denominator in parentheses to really show, to be sure. So that second answer now, we can go all the way back. How long will it take to reach 50 degrees? We've got right here. About 40.4 minutes for that one.